So, in this lecture, we are going to look at a very brief review of quantum mechanics. As I said in my prerequisites, I already assume that you know quantum mechanics very well. So, I won't be going into the very detailed part, but we need some aspects of quantum mechanics. So, I think this lecture will do a very good job for us to revise quantum mechanics. So we'll basically look at the simple harmonic oscillator. Just in order to be very specific, it's non-relativistic approach. So we'll start with the by writing the Hamiltonian operator. So the Hamiltonian of one-dimensional oscillator is given by 1 upon 2m p square plus m square omega square x square. So this is equation 1.1. Just a side note, I will be using the same equation as I'm using in my notes. I have a set of notes which I prepared for the lecture. So I'll be using the same kind of equation number which I have used in my notes. So yeah, this is p square. So this is the Hamiltonian of the one-dimensional oscillator. So now let's represent a cap be the annihilation operator and a gap dagger will be the creation operator. So I'll define my annihilation operator as 1 upon under root 2m h cross omega p cap minus I m omega x cap. So p cap and x cap are again the operators. This is 1.2. And furthermore, I define the creation operator. Okay, put a hat on it. 1 upon under root 2m h cross omega p cap my plus I m omega x cap. This is equation 1.3. So I can calculate a cap a dagger. So this you can see easily is given by E cap minus I m omega x cap p cap plus I m omega x cap. So the order in which you calculate matters in quantum mechanics. So we won't do any gymnastics with that. So I'll just take this equation over this side. So that will make our life easier a bit. Oh yeah, I forgot to name this equation. This is equation 1.4. So yeah, this is a b square. So I'm just multiplying this with this b square plus m square omega square x hat square. Oh, forgot to put the hat on it. It's fine. Plus m omega h cross. So this is equation 1.5. Okay, so now we'll do the same thing, but we'll calculate a dagger a. Here we calculated a dagger. Now we'll do with a dagger a. So this will give us an identical result, but just this sign will change. So let me write it fully. H cross omega p cap plus I m omega x cap p cap plus, okay, sorry, minus I m omega x cap. This is 1.6. So I'll take this 2m h cross omega this side and multiply this parenthesis. So we will get A dagger A B cap square plus M square omega square x square minus m omega h cross. So this is equation 1.7. Now, what I do is I'll add this equation 1.5 and equation 1.7. So let's do that. We adding equation 1.5 and equation 1.7. I will get A dagger A. So I took this as the first and we had A dagger. This will give me 2p cap square plus m square omega square x cap square. Since this is minus m omega h cut and this is plus m omega h cut, so they both cancel out. So this is what we are left with. So I'll get this 2 here and get this 2 here. It's just a rearrangement. I'll take this 2m to this side and get this 2 over this side in the denominator. I forgot to put a hat on everything. Plus a dagger is equal to 1 upon 2m e square plus square omega square x square. So this is my equation 1.8. So if I compare this equation 1.8 with the above equation of 1.1, I can write my H operator H cut omega by 2 A dagger A plus A dagger. This is my equation 1.1, and if you see, my Hamiltonian operator is simplified to this. So what we have done is we have written the Hamiltonian of simple one-dimensional oscillator in terms of creation and annihilation operator. Now this form is very useful for us, so we will use this. Okay, so that's why I boxed it. So now what we want to do is, okay, so they actually satisfy the following commutative relationship. Let's find A dagger. We want to find this. Okay, so we can actually write the commutator of A dagger to be equal to minus A dagger A. And we want to find what is equal to. We can do that. We'll go step by step, so I won't be rushing. So we'll calculate this term first and we'll calculate this term second, and then we'll subtract each other and we'll get the answer. So we'll go step by step. So we'll calculate A dagger 2mh cross omega p hat minus I m omega x cap multiplied by p cap plus I m omega x cap. So let's open this bracket. 2m h cross omega will get p square plus m square omega square x square plus m h cross omega. So what I'll do is I'll take this to be one term and this to be the second term, and multiply this into this so that this cancels out here. Okay, so we can do that. 2m h cross omega p square plus m square omega square x square plus half m omega. So this cancels out. We are left with half over here. So this I'll call it as equation 1.10. Okay, if we do the same thing, just repeating the same algebra, but for this time we'll do it for a dagger a, we'll find this to be equal to p square plus m square omega square x square minus half. So this is my equation 1.11, and from, yeah, if I have this, yeah, so now I can substitute this value here and this value here, and we can clearly see, okay, what happened, okay, yeah, so we can clearly see the commutator of a dagger is nothing but half plus half. This implies my commutator of a dagger is 1. This is my equation 1.12. This is one of the most important commutation relation that you'll encounter in quantum mechanics. So what we can do is, why did I calculated this in the first place should be your question. You see, we can actually use this commutation relation to rewrite the Hamiltonian that we just derived in terms of creation and annihilation operator. That will simplify our Hamiltonian even further. Okay, let's do that. So, okay, let me open this commutator a dagger. This is nothing but a dagger minus a dagger a. This is equal to 1. So what I can do is I can rewrite this as a 1 plus a dagger a, and I will use this to rewrite my Hamiltonian that we just derived. H hat was, we derived this just above. Okay, h cross omega 2 dagger a plus 1. So this is nothing but h cross omega. I'll just multiply this half inside and we'll get a dagger e plus half. So this is my Hamiltonian operator for one-dimensional oscillator, even simplified. This is even more simplified than previous one. This is awesome, right? This is awesome. What now we can do some interesting stuff. What we can do is we can calculate the commutation relationship between this Hamiltonian operator and this number, this annihilation operator. Okay, let me be very clear about this. So A is the annihilation operator and a dagger is the creation operator. Dagger creation, annihilation doesn't have a dagger, so you can remember in that way. So that will be even more simpler for you. Okay, let's do this interesting task that we have in our hand. We want to calculate HA minus AH. So we'll use this H cross omega a dagger a plus half a dagger minus a dagger. Okay, minus A, let me very A dagger A plus half. Okay, so I can carefully open this bracket. So A dagger A plus A by 2 minus A dagger A minus A by 2. So this 2 cancels out. What I left with is I can take the minus sign outside. You will see why. You will see why. A dagger A minus A dagger A. Okay, I'm missing the hat on everyone. Okay, so you can see that if I take this common, A common from the right hand side part, so this is nothing but the commutative relation between A and A dagger, and we calculated this to be 1. So this is nothing but minus h cross omega A. So we see that the commutation relation between the annihilation operator, between the Hamiltonian operator and the annihilation operator reduces by 1/8. This is the answer. So I name this as equation 1.4, and we can do the similar calculation with A dagger, the Hamiltonian operator A dagger. Hamiltonian operator A dagger minus E dagger H, and this is H cross omega. Okay, let me be very careful in writing this, plus half A dagger minus A dagger A plus half. And if we open this bracket, we will have H cross omega A dagger A plus A dagger by 2 minus A dagger A minus A dagger by 2. So this both cancels out. Again, the same thing happens. We'll take A dagger common, and we're left with this commutation relation between A and A dagger, and we already know that this is equal to 1, so this is nothing but A dagger. And this is equation 1.15. So this relation, so we done this fun part. So this relation implies that if is an eigenstate of H with eigenvalue. I assume you're already familiar with what is eigenstate, eigenvalue, E subscript n. So I can write it H n E n. So what this means is this is the eigenvalue. This is the eigenstate. So an operator, the H operator, acts on the eigenstate, gives us an eigenvalue, and gives us the same state back. So the states an. So yeah. So this implies that the states an and a dagger n are also eigenstates. So this is one of the fun exercise that we did, and this gave us the result back. So now why I have done this, you see, we can rewrite this H operator. Now what I can do is I have this state n. I can operate this Hamiltonian operator and the annihilation operator on this state in this respective order. So we know that from we calculated this from our fun exercise. We got this as HA minus AH to be equal to minus H cross omega A cap, okay, A cap. So I can rewrite this again as A minus H minus omega A. So okay, I can use this to write my H hat A hat acting on this n to be equal to En minus H cross omega A n. So the operator, now okay, let me name this and let me explain it to you. This is equation 1.17. The operator, the annihilation operator seems to annihilate a quantum of energy of an amount h cross omega from the state. This can be seen clearly. This is the eigenvalue. So what this operator, this annihilation operator acting on this eigenstate is doing is that it reduces the operator A hat. This annihilation operator seems to annihilate a quantum of energy. What is a quantum of energy? H cross omega is quantum of energy. Is in particle quantum mechanics, this is used as a familiar terminology. Quantum of energy by an amount h cross omega from this state. Similarly, if we do this, if we do a similar exercise for h a dagger n, we will find En plus h cross omega A dagger n. This is my equation 1.8. So the operator A dagger, which we call as creation operator, creates a quantum of energy. So now I think you understand why it's called the creation and annihilation operator. So this A operator acts on this eigenstate, reduces the state by a quantum of energy by an amount h cross omega. This creates a quantum of energy. So in any physical process, energy must be conserved so that the operators A and A dagger cannot appear alone in the expression of any measurable quantity. It always appear in pairs. You see this in anywhere in quantum mechanics. The ground state. Now let's move on to the further. So the ground state is denoted by 0. So this is ground state. So if the annihilation of, so okay, the ground state is, just to be clear, this is the state of lowest energy. So this is the state of lowest energy. It's called ground state in quantum mechanics. If the annihilator operator, okay, if the annihilator operator acts on this ground state it cannot produce a state any lower than this energy. This state must be totally annihilated by the operator A hat. Okay, this cannot produce any lower energy than this. That is why A hat, this annihilation operator, must totally annihilate the state. So this will be our equation 1.19. So the energy eigenvalue, okay, we can find this. It's very easy. So the energy eigenvalue can be it can be found by using this familiar equation that we have derived in this lecture. Acting on zero eigenstate will give us h cross omega. So the eigenvalue, this is the eigenvalue of the ground state. So what does this mean? Oh, okay. Classically, we can have zero energy, but quantum mechanically, for one-dimensional oscillator, we cannot have the zero energy. The zeroth energy state corresponds to non-zero energy, which is half h cross omega. So you might have studied when you might study the quantum mechanics as your first course, you might be seen baffling by this particular derivation. This is one of the equations that's been used everywhere in quantum mechanics. No matter wherever you go in quantum mechanics, this is used. So this is one of the most beautiful equation. It states that the quantum mechanically you cannot have zero energy. There is always some energy in the quantum in the form of fluctuations maybe. So many of the concepts are used in various aspects in theoretical physics and all. We won't be going much into the details, but this is necessarily one of the starting point. So uh, okay, let's see. Okay, so this I will name as equation 1.20 because this is one of the used equation. So I want to know the first excited state. So let's want to know first excited state. So we will denote the first excited state by 1. So it can be defined by the state whose energy is larger than the ground state by 1 quantum. Okay, so we can represent this as 1 uh, larger. Okay, we can define the first excited state whose energy is larger than the ground state by 1 quantum. So as we said earlier, A had A dagger is the creation operator. It creates a quantum of energy. So this fits what I said perfectly. So this is equation 1.21. Similarly, we can have the knowledge of nth excited state. Okay, nth excited state. Again, to be very clear, provided it's normalized, we can define it as n 0. So this is equation 1.22. So this equation gives us the nth oh my god. Okay, it's fine. I messed it up here. So I hope you understand. So this equation gives us the nth state. So one thing which is essential to realize is the need for normalization. Normalization constant. So I said normalized. So one thing we have to realize is the need for normalization constant. See, Since the total probability is always has to be 1, it is essential to have the normalized constant which will make sure our total probability goes to unity. Okay, so from this equation, so what we can do is from this equation 1.22, we can see that the first excited state, okay, is this. The second excited state can be, we are writing it explicitly, 2 factorial square. Yeah, what I mean by square is it is operated twice on the ground state, or else we can, just to be short, we can write it as 1 by 2, 1. Similarly, we can do it for, okay, similarly, let me write it for 3 as well, so we'll have a better understanding. 1 upon 3 factorial. We are just plugging numbers in this equation, nothing more than that. 3, 0. This can be further written as 1 by root 3 a dagger of 2. So this can be equation 1.23. Okay. So now what we can do is, so we can easily write the nth state. Okay, let me write it down. We can easily write the nth state in terms of, I hope you can see the pattern. Okay, here, okay, in terms of n minus 1th term. So here we have nth term, here we have n minus 1th term. So we have n, if n is 2, this is n minus 1, which is 2 minus 1, which is 1. So if n is equal to 3, we have 3 minus n minus 1, which is 3 minus 1, which is 2. So that what, so this shows a pattern. We can easily write the nth state in terms of n minus 1th state. So the energy eigenvalue, okay, the energy eigenvalue of the state can be written as E subscript n to be n plus 1 half h cross omega. So this is one of the most important equation. So how do I obtain this? So detailed solution of this we will, so this can, I have some problems actually. So this can be seen, okay, yeah. So the detailed solution of this is, we will do it in exercise 1.3. So this was a brief overview of the quantum mechanics that we might need. So let's go to some problems. I have about 3 problems. We'll solve these 3 problems and later on, yeah, so we'll move ahead with these problems. Okay. Okay, so what does our first problem says? Oh, okay, it's not visible, I think. Yeah, I'll just move it down. Okay, so, oh, mm, okay, let me correct this and I'll get back. Just a second. Okay, so what does our first problem say? So our first exercise is, if the ground state is normalized. What do I mean by normalized? Okay, so should I mention it? So this is equal to 1. So if the ground state is normalized, that is this. Um, is equal to 1, show that the excited state is defined by equation 1.22. So okay, so what was equation 1.22? Let me refresh your memories. Okay, I'll write the solution, maybe that would be better. Solution of exercise 1.1. Okay, let's go. We are given that the ground state is normalized. Okay, so this is what we are given. And we want to show, what we want to show is, and defined by this equation also normalized. We want to show that a, okay, we want to show that it remains normalized. The nth state also remains normalized. So okay, we'll start with equation 1.22. So let's refresh your memories. Equation 1.22 was 1 upon n factorial square under square root a dagger n 0. Okay, so yeah, so we know that we can also write this as, you know, this from quantum mechanics. It's not a big deal. It's, you know, this from quantum mechanics. Okay, now what we can do is we want, okay, we can calculate this 1 upon n 0 n a dagger n 0. Um, so we know that the first excited state is written as this, and we know that the second excited state can be written as, uh, okay, what I'm doing is I'm just plugging numbers in this equation. What just happened? Yeah, 1 upon root 2 factorial a dagger 2 0 is equal to 1 upon root 2 a dagger of 1. Okay, a dagger of the first excited state. Now, what we can do is write 3. I don't think so. We don't need it. Yeah. So the nth state can be written as 1 upon n factorial. Oh, okay. N a dagger n minus 1. Okay. Equation 1.5. So we can rearrange this. Okay, what we can do is we can rearrange this a dagger n minus 1 root n n. Now, I'll do a very clever trick. Okay, what I do is I'll define n minus 1 to be n. Okay, so this will imply my n would be n plus 1, right? So in this case, I can rewrite this a dagger as n plus 1 n plus 1 at state. So this is just a trick that we use frequently in our quantum mechanics course, and we can write an as n minus 1. So this is equation 1.26. So okay, so we have a dagger operating on n and a operating on the state n, and this is the values that we have currently. We can use this in our equation. Okay, yeah, we can use it over here. So let me write this. So we will have 0 is n factorial 0. Similarly, we can calculate the bra vector as well. This is ket, this is bra. You know that from quantum mechanics. N 0 n factorial. So I can calculate a n a dagger n 0. So So this becomes n factorial 0, 0. So we already know that this is equal to 1. This implies, okay, so this implies my n. Okay, so I can use this, and this implies I can calculate my, so you recognize this, right? This is just this. Where did it go? Okay, we have this. Now we know that the value of this is n factorial that we just calculated from this, and so this is n factorial. So this and this cancels out. This implies n is equal to 1, which implies it is normalized for nth state. Brilliant, brilliant. We did it. Thus, we prove that the excited state are also normalized. Let me write it down. This implies excited states are also normalized. Brilliant. Okay, so we did our first exercise. That's a bravo. That's a kudos to us. Kudos, man. Now let's do the second exercise. What does it say? We have the number operator is defined as this. So yeah, this we know from quantum mechanics again. So I'm telling a lot of because I assume that you know quantum mechanics, or else studying QFT will be the hardest thing that you'll ever do. So it's better you go and revise quantum mechanics very well. If you don't know, it's fine. If you don't know, then I don't think you should be here. So show that its eigenvalue in the state n is n. Okay, we can do this. It's a very simple exercise, just 3-line exercise. Okay. Solution to exercise 1.2. So the number operator is defined as n. This is curly n, a dagger a. So we have been asked to show that its eigenvalue in the state n is n. So if this operator acts on the state n, its eigenvalue should be n. So we can do this. It's a very simple exercise. A dagger A operating on n. So as I said, order matters in quantum mechanics. So first, this A annihilation operator will act on n. So we know this to be root n, n minus 1. So we can, n is, okay. Now A dagger will act on the n minus 1th state, and this will give us, we know that we calculated it in the exercise 1. Okay, just to remind you where it is. Yeah, this, okay. We calculated this. Okay, so we can use this here. So this will be root n n. So this is n n. So we just showed that the number operator n acting on the state n has the eigenvalue n. Okay, so this we proved. So this is equation 1.28. So we did it. It's a very simple exercise. Pick very simple exercise for you guys so that you don't feel discouraged. You won't feel discouraged. So now we can, yeah, the third exercise is even more simpler. Show that the energy eigenvalue of, okay, yeah. So we have to show that the energy, okay, there's a typo here. Can show the energy eigenvalue of the state n. We can do that. We know we can do that. Yeah. Let's solution for exercise 1.3. So yeah, so the H operator acting on n is, we know this to be, this is what we have done in the whole lecture. A dagger A plus half n. on the state n. So this acts on the state n. And we can just split it out. A dagger A acting on n plus, so this multiplies with this comes here, h omega by 2 n, state n. So this can be written as h cross omega. We know this to be equal, this is nothing, okay, if you didn't recognize it, a dagger, I'm making mistakes, wow. So this is nothing but the number operator that we just did it in the exercise 1.2. So this we calculated to be equal to n, right? So this is n plus half, right? So what did you just see? This is the eigenvalue. This is the eigenvalue. This is En. We just saw En to be equal to h half plus n h cross omega. This we all, so as I said, this is very simple. So this is, so yeah, this is what I just said, that we'll do it in exercise 1.3. So that's it for this video. In the next video, we'll see the special relativity. We'll be focusing on the mathematical structure for special relativity. And also I'll be doing few exercises to help you guys out so that you get familiarized with the notation and all those stuff. And then I think we can move on to yeah, before going to natural units, I have to cover one more topic with the examples. I'll do it in the mathematics structure of special relativity itself, just to introduce some few notations. So yeah, I think we are done with this lecture. Thank you so much for attending this series. I hope you enjoy it. Thank you so much.